Got all of them. So hello, everybody. Thank you so much for joining us. Okay, I just got the go ahead to start. I was just going to give a quick hello, but let's get going then. So thank you for joining us for this week's SEDS Online webinar. My name's Chelsea, and before we get started, I'd like to thank our sponsorship from the IAS, which allows us to offer all of the resources to you free of charge. All of the webinars, of course, you can see them all, the recordings up on YouTube, as well as lots of other resources up on our website, so make sure and go and check that out. There's recorded lectures, different learning tools, virtual field trips, all that sort of stuff. So make sure and yeah, go and take a look. Today's lecture is by Dr. Giovanna Della Porta, who's a carbonate sedimentologist and an associate professor at the University of Milan. She's also an editor of one of the IAS journals, Sedimentology, and she has semi-recently, let's say during sort of COVID times, along with Paul Wright, created a really great, another really great free resource for sedimentologists called Carbonate World, which focuses really on sort of the petrographic characterization of carbonate rocks. So go and check out carbonateworld.com as well. A little plug there. It's really great. So I really highly recommend it. Giovanna got her PhD from the Vrije University in Amsterdam, and her research focuses on all things carbonates, working from everything in marine systems all the way to travertines. So we're really happy to have her, and her specialization is on microbial carbonates, which we'll hear about today, and sort of something near and dear to my heart. So I'm extra excited for this presentation. And with that, Giovanna, I will give you the floor, and good luck.
Thank you, Chelsea, for the introduction. Good afternoon, everybody. I would like, first of all, to thank the SEDS Online team for inviting me to give this presentation and for keeping on this important tool that offers important service to the sedimentological community. I would like to give today a presentation that actually is nearly 20 years old in terms of content and slides, even though I have updated the material. And the content of this presentation focuses on the results of my PhD. That focuses mostly on microbial carbonates on carbonate platform outcrops across the geological record. Because this presentation, as I said, is 20 years old, I have first of all to make credit to the people that drove this project on high relief carbonate platforms, and is Wolfgang Schlager, who was my PhD supervisor. And most of all, the project focuses on interaction between academia and industry, driven by Jeroen Kenter at the time at the Free University in Amsterdam, and Mick Cherries from Chevron, and other geologists and sedimentologists from Tengiz Chevroil. The results of this PhD brought some important concept on the interpretation of high relief carbonate platform with microbial boundstone that are used nowadays. And I thought that for younger generation was important to go back to the original studies and references and show how we got to this concept, mostly based on lots of field work, outcrop studies, and use of outcrop analog to understand subsurface hydrocarbon reservoir. Here there is a list of people who I would like to thank, who work with me in the field on some of the case studies I will show you. The other reason for this presentation that is more than 20 years old is actually a new publication that is a book of field guides to exceptionally exposed carbonate platform outcrops that has been recently published by IAS. I am Paul Bright, the editor, and Elias Samoncasos is the series editor. This book collects 13 field guides to carbonate platform outcrops from the Devonian to the Miocene, and actually 7 of these case studies are well-exposed carbonate platform with microbial boundstone at the platform margin. Therefore, it is a good occasion to have this presentation on this topic and also advertise this book that is a collection of very detailed field guides that will hopefully help a lot of people to visit by themselves these outcrops and learn from them, as I did during my PhD and my following years of studies. I have to specify that actually this book is the result of was published in 2021, but it is the result of a project started many years earlier by Andrew Hurst, Jeroen Kenter, and Stephen Graham, and actually was a project organized for APG. Paul Wright edited most of the carbonate platform field guides, and the result of this project ended up in a special issues for the APG bulletin in 2017, but then a collection of field guides was never published, and that's why some years later Paul Wright and I, with Elias Samankasus as series editor, reproposed this volume. Now, here you have the content of this field guide book. If you are interested, please contact Elias for the details to get the individual publications or the whole book. There are 13 case studies, but the first 7, as I said, are focused on platforms that have an important microbial contribution that will be part of this talk. Now, what can we learn from these outcrop studies? Are all examples of high relief platform, as I said, with a significant percentage of carbonate rocks produced by microbially mediated precipitation, and this microbial boundstone occur mostly at the margin of this platform. We can learn looking at these carbonate platform outcrops that microbial carbonates are rare to sparse in the Phanerozoic, but actually dominated in certain specific time period following crises of skeletal biota, extinction events, or changes in environmental parameters that negatively affected the skeletal factory. And these carbonate platform with microbial boundstone are actually most abundant in the time period from the late Palaeozoic to the early Mesozoic, Triassic, and Jurassic. These platforms are all characterized by these reefs dominated by microbial boundstone associated with various skeletal biota that contribute heavily to the growth of this high relief platform, hundreds of meters high, that can propagate for several kilometers. And most of the carbonate production is actually related to this carbonate factory in situ on the slope from nearly water depth that are dysphotic to aphotic, nearly 300-400 meter water depth on the slope. And what we can say is that these microbial boundstone-dominated high-relief platforms are non-actualistic, non-uniformitarian carbonate platform, different from typical present-day tropical light-dependent photozoan platform. So the conclusion of this review is that in carbonate sedimentology, we all know that when we look at the geological past, often the present is not the key to this past, but the present can help to understand some of the features that we observe in the geological record. The key message of this presentation are actually, as I said, studies that are nearly 20 years old, and there are 2 major concepts that I would like to focus on: the microbial carbonate factory, we know from the classification by Schlager, represent a distinctive type of carbonate platform production with distinctive profile of accumulation versus depth and platform geometry, as Wolfgang Schlager clearly represented in his classification of the three carbonate platform, differentiating a tropical photozoa carbonate platform where carbonate production is maximum to water depth of the euphotic zone and then decreases exponentially, becoming nearly zero, and this in the aphotic zone, and this is mostly related to carbonate production linked to light dependent autotroph organism or organisms that have photosymbionts. For the microbial carbonate factory, we know that carbonate production is often light independent and can continue to depths that are 300-400 meters in aphotic zone. Schlager clearly evaluated that this carbonate production profile versus depth characterize specific carbonate platform geometry, and the microbial carbonate platform, called also the mount factory or mud mount factory, can provide geometry as mud mounts or high relief platform, different from the tropical one. The other concept that derived from this classification of Schlager is more related to the case studies that I'm going to present, and I have evaluated some of them during my PhD under the supervision of Jeroen Kenter and with the help of Mitch Harris, and that is that this type of microbial carbonate factory grows in situ on the slope down to 304 meter depth and creates depositional system that respond differently to changes in accommodation with respect to tropical platform. And this type of behavior has been synthesized as slope shedding model. The concept of the slope shedding model, that is the main conclusion of this presentation, so these slides will come back at the end of my presentation, show the comparison between a classical light-dependent photozoa and tropical platform, the tropical carbonate factory of Schlager, with a reef bioconstruction limited to shallow depths within the euphotic zone. The high relief platform has a steep margin and a slope that is sourced partly by the coral reef at the margin, but largely from platform top derived sediment. This type of process was defined in 1994 by Schlager as the high standard shedding. The model of the slope shedding that characterized mostly late Paleozoic, but also early Mesozoic high relief platform with microbial boundstone at the margin consists of a carbonate system where the carbonate factory on the slope extends down to 300-400 meter depth, and most of the slope is actually sourced by the boundstone, the microbial boundstone in the upper part of the slope that produces the triatal breccia forming the lower part of the slope. This type of carbonate system has a limited, you see the small arrow, input relatively reduced with respect to the microbial boundstone on the slope from the platform top. And this slope can grow, prograde extensively independently from the high stead shedding of grainy and mud from the platform top, because the carbonate factory is directly in situ on the slope. This concept has been summarized as a slope shedding model, and one of the key features is that because the carbonate factory is on the slope in a depth window extended to 300-400 meters, the behavior of this carbonate platform with respect to changes in accommodation space in relative sea level is different from tropical carbonate platform. And platform progradation can occur during every sea level stand independently from high state shedding from the platform top. So this presentation aims to show you case studies that confirm this model of the slope shedding. But before getting into the geological record, I would like to say a few things about microbial carbonates using actually the knowledge that we have from the present. So trying to apply the uniformitarian concept. From the present, we learn that carbonate precipitation driven by microbial biofilm takes place through different processes, and it is the byproduct of two main types of mechanism, either an active precipitation where the precipitation is linked to microbial metabolism, and this is called biologically induced precipitation, but there is also a considerable amount of carbonate precipitation related to passive mechanism of non-living organic matter that can derive from the extracellular polymeric substances of the biofilm that have the capacity of binding calcium ion, or from sponge bodies. And this type of carbonate precipitation that does not require a direct microbial metabolism is defined as biological influence precipitation. What we know from the recent is that there are various mechanisms of carbonate precipitation driven by interaction with microbial biofilm that are not light dependent, and this justifies the fact that the microbial carbonate factory can extend to a photic depth on the slope of platform. Then from the recent, we learn also that there are microbial carbonates nowadays in various depositional settings, from marine to non-marine setting, shallow setting in the marine environment, from intertidal to supratidal, continental setting from freshwater to hypersaline and alkaline environment, or even in the deep biosphere. In all this setting, microbial precipitation is actually controlled by some important parameters. First of all, the water chemistry and the high supersaturation, the lack of skeletal biota competition and the availability of substrate. And as we said, many mechanisms that drive carbonate precipitation are light independent. We also know from the recent, and then comparing it with the geological past, that at the microscale, microbial carbonates are fairly similar from the fossil record. These are examples from the Carboniferous, these are examples from the Pleistocene, but also from the recent, both marine and lacustrine records. So at the microscale, it is difficult to distinguish exactly the depositional environment of these carbonates. And the difference between the fossil record and nowadays is that nowadays we can have several meter scale buildups in a lacustrine setting, but in the marine environment, we observe millimeter to meter size microbial carbonates. Instead, if we look at the geological record, we see that microbial carbonates could develop decimeter to meter to hundreds meter or kilometers carbonate buildups. So the geological record shows us buildups as mound on carbonate ramps, or hundreds of meter thick succession of microbial boundstone on the margin of carbonate platform that can prograde for several kilometers, and we don't see this nowadays in the recent. So the question that I anticipate now, and then I would like to conclude, is that maybe it works both ways, and the geological record actually can also help us to understand the present, and maybe also to predict the future and possible responses of carbonate system to future environmental perturbation. Now, going back to our case studies and the core of this presentation, this diagram shows the key case studies presented in this volume of the field guides that include examples of microbial carbonates are here indicated in blue, and the bars show their temporal extension through time from the late Devonian to the Jurassic. And I have compiled this diagram to show how this microbial dominated carbonate platform developing in a general global context, mostly occurring during periods of important extinction events, here indicated with this arrow in purple. This is the extinction event at the end of the Devonian, Franian, Phanerozoic, and also the Hagenberg event at the beginning of the Mississippian. And also you can see, comparing the distribution of the case studies I will show you with the general reef composition across the Phanerozoic. This portion of the diagram shows with the wider areas the times when reefs and bioconstruction were dominated by skeletal frame reef built in the Ordovician, Devonian, and then from the late Jurassic, and periods during which microbial carbonates dominated, forming mud mounds or microbial boundstone margin, and microbial carbonates were associated with various skeletal biota such as bryozoa, algae, sponges, and foraminifera. You see also that these case studies that I'm showing are linked with the intervals of alternation of calcite and aragonite sea, and actually fit mostly with the aragonite sea period between the late Palaeozoic and the early Mesozoic. And the important climatic changes during the Phanerozoic are also reported in this diagram, with the main glaciation in the Ordovician, Carboniferous Permian, and Pleistocene, and various studies showing alternation of warm and cool climate during the Phanerozoic. This is to explain this general diagram, but we will focus on example of these various case studies. The case studies here indicated in blue are those containing this volume that we will not consider because do not contain a dominant or major proportion of microbial carbonates. So we start from the example of the Canning Basin in the late Devonian, Leonard Shelf, and we focus on the portion of this carbonate platform occurring, accumulated during the Phanerozoic, so after the Phanerozoic Frasnian extinction event, and you can see that the carbonate platform could prograde for several kilometers, indicating that there was a very high carbonate production for this platform. And this is a diagram synthesizing the facies belt of the Canning Basin Phanerozoic platform. The color codes of the diagram is similar for this and the future diagrams. In green, there are reported the platform top lithofacies. In pink purple is indicated the margin and the upper slope dominated by microbial boundstone. In darker blue are reported beds of breccias that dominate in the lower part of the slope. In light blue, resedimented material of greenstone and paxton, and then in gray, fine-grained sediments that form the basinal strata or that might occur even on the slope. What you see from this profile is a horizontal platform top with the lack of a raised rim, but outer platform beds deep in basinward, a steep slope with a microbial boundstone factory associated with sponges, brachiopods, calcium microbes, and abundant marine cement extending from nearly 5 meters to 150 meters paleo water depth. Laterally adjacent to breccia, reworking this upper slope boundstone. The second case studies is a Pennsylvanian carbonate platform in northern Spain. That was the main focus on my PhD. And this carbonate platform is quite famous for the type of outcrop because tectonic tilting in the Cantabrian Mountains, Hercynian orogeny, tilted the platform and all the stratal pattern vertically. So from aerial photograph, it is possible to see the bedding, and these red lines that you see here are actually DGPS walked strata by several people, not only me, and all the colleagues that worked on this platform are reported in this publication. As you can see from this aerial photograph, so we are looking from above, we have subhorizontal here strata indicating the platform top that are parallel with basinal strata, and some oblique lines. These lines represent the slope clinoform connecting the basin and toe slope strata with the platform top. This platform has an age developed mostly from the Bashkirian to the Muscovian, and looking at the clinoforms on the slope and the lateral migration of the platform break, of the platform margin, we can see that the platform had a rapid progression of nearly 3 kilometers during the Bashkirian, and then a Muscovian aggradation. If we overlap facies mapping on this aerial photograph, we have the image below here where we see that the upper part of the slope clinoform is dominated by microbial boundstone associated with bryozoa and abundant marine cement, and lateral to the upper slope microbial boundstone there is a lower slope dominated breccia. The slope clinoform are planar to concave upward. And this is the similar diagram showing the reconstruction of the facies distribution with an outer platform with basinward dipping of the platform beds, microbial boundstone dominated upper slope down to 300 meter depth, lateral to grain supported cemented breccia, and a concave upward toe or slope. This outcrop, as you can see, is mapped here, can be observed from some panoramic viewpoint that give the can show all the facies belt represented in this mapping. If we could, in this moment, be in this position where the red dot is, the image that we will see is the panoramic view represented here with, on the right, so towards the south, the basinal deposit. On the north, well-bedded, the platform strata, and all this area where bedding is not too well visible, but there are some inclined beds, is the Bashkirian slope that is progressing towards our view point. And here, in this point, we see the transition from the outer platform, slightly dipping towards the basin, and the upper slope dominated by microbial boundstone. As represented again in this diagram, all the microbial boundstone are this pink and purple area, and they consist mostly of this clotted peloidal micrite forming this centimeter size accretionary growth form with centimeter size primary voids filled by botryoidal aragonite cement. In this section, we see microsporite and clotted peloidal micrite associated with phenestellid bryozoa, botryoidal aragonite, and calci microbes like Renalchis. This upper slope boundstone is lateral to lower slope grain supported breccia that are cemented. There is a lack of matrix in the lower slope breccia. In some cases, there is some clotted paleoidal micrite microbial bounding even in the lower slope breccia. This Sierra de Cuera platform in Asturias was used as outcrop analog of another platform, this time in the subsurface, dominated by microbial boundstone in the upper slope. This is the Tengiz field in the Pre-Caspian Basin, an isolated platform with a steep planar to concave upward slope that in the upper portion is dominated by this microbial boundstone. In particular, during the Serpukovian, here in the eastern margin, we see that the platform progressed for several kilometers. And if we make a diagram, a sketch of that portion, we see also the reconstruction of the facies distribution. We see another platform dominated by Paxton with brachiopods with beds deep in basinward, an upper slope microbial boundstone in situ down to nearly 300-meter water depth, lateral to lower slope breccia, as similarly we saw in the outcrop case studies. And a detail of the Tengiz upper slope boundstone is shown in this core image with irregular laminated accretionary growth form made of clotted paleoidal micrite associated with fenestellate bryozoa, isolating centimeter-sized primary cavities filled by botryoidal aragonite, and some porosity in this case is still open. Now, following the Carboniferous, another case studies that shows my important contribution by microbial boundstone is the Permian Capitan Reef in the Guadalupe mountain, and also in this case the massive reef the margin and on the slope can extend to nearly 150-100 meter water depth and allowed the progression of this platform for several kilometers, up to 19 kilometers in the Delaware Basin, a starved basin with an evaporatic deposition. And also in this diagram we have the sketch representing the Middle Permian Guadalupe mountain reef with the microbial boundstone reef associated with calcareous sponges in the upper slope down to depth of nearly 200 meters, adjacent to grain supported breccia, highly cemented and matrix free, and the progression of this slope was for several kilometers up to 19. This is studies of the 19 on the composition of the Capitan Reef, showing the association of calcareous sponges with several types of microbial crust and calcium microbes like Archeolitoporella and Bryozoa, with abundant aragonite, botryoidal aragonite, and radiaxial fibrous cement, as in the other microbial slope. Then after the Permian Triassic extinction event, there are several case studies of the Triassic that show an important contribution in the field guide volumes. 3 of these case studies are reported from South China and from Northeast Italy. The example of South China, the Great Basin Guizhou, there are abundant contribution of microbial boundstone with sponges and tubiphytes in the boundstone of the lower reef. And instead, if we move to the case studies that are more familiar to me in Northeast Italy. There are microbial slope in the Dolomite. These are 3 outcrop examples of the middle to late Triassic Dolomite archipelago. Here in the map, they represented the position of the Latemar platform, that is this one, the Sella and the Marmolada. And in this profile, you see the horizontal platform top, the platform break, and the slope clinoform. And in this area of the Latemar, there is an important contribution of microbial boundstone precipitation, and the same for the Sella platform. You see the platform break and the rapid progression of the Sella clinoform. The Sella platform was studied by Schlager and Keim around 1999-2000, who first identified that a significant portion of the upper slope clinoform, planar clinoform of the Sella were dominated by clotted peloidal micrite due to microbially mediated precipitation lateral to grain-supported breccia. More recent study by Nereo Preto and others from the University of Padova and Piero Giannolla from the University of Ferrara focused on both the Latemar, here represented, and the Sella, showing similarly that the upper portion of the slope is dominated by microbial boundstone associated with sponges and tubifides. And they presented in this field guidebook the comparison between the Anisian Latemar platform and the Carnian Sella platform, both dominated by microbial boundstone on the upper slope, with the difference that in the Latemar, the lower slope is dominated by grainstone paxon of grainy resedimented material, and in the Sella, the lower slope is dominated by grain-supported breccias with clasts mostly derived from the upper slope boundstone. The other difference is that during the Carnia, on the Sella, there is also a coral reef developing that creates a certain raised rim on the platform top that we don't see on the Latemar, where the outermost platform beds are deep in basinward as the other microbial platform I showed you. Then there is the addition of another case studies closer to where I am at the moment in Milan, of the Esino limestone. The Esino limestone is less famous than the Dolomites, but basically it represents an archipelago of isolated carbonate platform, here reported in yellow, of the same age, Anisian Ladinian of the Latemar, that were able to prograde for several kilometers, and with upper slope microbial boundstone with huge cavities filled by botryoidal aragonite cement. This is an image. Here there is the hammer for scale. These botryoids are actually 30-40 centimeter in diameters, are dominated by botryoidal aragonite, and these large cavities are sustained by microbialites consisting of laminated and clotted peloidal micrite. In some cases, botryoidal aragonite is followed by radiaxial fibrous calcite. And also these platforms are, in some cases, exposed very well with a huge view of the platform slope. Another example from northern Italy that I would like to show is the case of the Dolomia Principale, the Norian, that in the Lombardy Basin during the Norian was characterized by the development of intra-platform basin, here indicated with this violet color. This basin, driven by sedimentary tectonics, dissected the laterally extensive early dolomitized Dolomia Principale platform, here indicated in yellow. At the margin of this intra-platform basin that must have had quite a restricted circulation and probably high salinity, there are microbial boundstone developing. Here, an example of this columnar laminated microbial boundstone that can extend on the slope. And this is a particular case of development of microbial boundstone because different from all the other case studies that were related to following extinction event, actually during the late Norian, in other location towards the open Facies Ocean, I am referring to Austria and the Austro-Alpine carbonate platform, the Dachstein shelf, there were coral reef developing. In the case instead of this restricted basin with limited circulation and probably high salinity, instead microbialites predominate for the availability of substrate. So after the Triassic, there is an important extinction event at the Retian and Tangian boundary, and the lower Jurassic platform show a mixture of microbial boundstone and coral reef. The example that I have studied with all my colleagues listed here is in Morocco. The Jebel Boudar is again a high relief platform with a height from platform margin to basin of nearly 450-600 meters, visible on outcrop, and a steep slope up to 30-degree steep. The Jebel Boudar carbonate platform had a complex vertical evolution, started from as a low angle system with ramps and mud mound on the ramp, and then developed a high relief geometry with microbial boundstone and coral reef at the platform margin. And two outcrop photos of these phases are shown here. The lower one shows the Sinemurian low angle ramp system with meter scale siliceous sponge mounts, and the upper photo instead shows the Plinsbachian high relief system with a slope up to 500 meters, and you see the platform top dipping basinward with a rounded platform margin dominated by coral reef and nearly 30 degrees steep slope. This Plinsbachian steep slope consists of different type of reef. In the deeper part, there are these microbial boundstone indicated with the darker pink lenses, and are dominated by Paleolithic micrite, siliceous sponges, and cement-filled stromatactis-like cavities, lacking corals. In the upper part of the slope, between nearly 100 meter and 5 meter water depth, instead the corals develop, but they are surrounded by microbial precipitation and are associated with stromatoporoid sponges. And here is another example of the Jebel Boudar coral microbial boundstone at the margin and on the upper slope, and in some cases also associated with some microencruster, Bacinella, and Lithocodium microbialite in the outermost platform. So I have gone through several case studies from the late Devonian to the lower Jurassic that show similar features, and they are all high relief carbonate platform dominated by a microbial boundstone on the upper slope. The slope is steep, nearly 30 degrees, with planar to exponential clanoform. The platform top is flat without a raised rim, and the outermost platform we can define as falling beds. They are deep in basinward, gradually connected with the upper slope boundstone. The growth of the microbial boundstone on the slope goes down to a photic depth above 300 meters. This slope all developed in settings with high supersaturation of seawater because they are all rich in early marine cement that increased the stability of this steep slope. The lower part of this slope consists mostly of matrix-free cemented breccia. There is very little detrital micrite because this type of platform produce less micrite than present-day platform, but also they all are late Paleozoic to lower Jurassic, so before the time the onset of calcareous plankton that could increase the amount of matrix on the slope and basin. And the detrital lower slope is mostly sourced by the upper slope boundstone rather than from platform-derived grains. All these common features brought to the development of this model of the slope shedding, where the carbonate factory on the upper slope allows high accumulation rate and progradation of this carbonate platform independently from the relative sea level changes and accommodation changes. So this goes back to the conclusion of this presentation and I hope all these case studies confirm that this type of carbonate platform from late Paleozoic to Triassic and Jurassic behave differently from light-dependent photozoa and tropical carbonate platform. And we can use this model of the slope shedding for this specific distinctive type of carbonate platform margin and slope. To conclude, going back to the representation of the carbonate factory proposed by Schlager and the comparison of the carbonate platform production profile versus depth, if we compare present-day tropical carbonate platform with a carbonate factory limited to the photic zone and developing a raised rim on the platform margin, we see that microbial dominated high relief platform have a rounded platform margin with basinward deep embeds and the carbonate factory extending to higher depth on the slope, which is the maximum water depth limit for the carbonate microbial carbonate factory. Actually, we do not know. We have seen in the various case studies, it varies from 150 to 350 meters. It might depend from decreasing saturation state of seawater or nutrients level, the depth of pycnocline or oxygen minimum zone. This still has to be investigated. But for my personal experience, I think that the saturation of seawater is very important. And in fact, when we do not see anymore the microbial boundstone in situ, we start to lose also the early marine cementation. And the other important thing to keep in mind is that microbial carbonate platform can be synthesized in this model defined slope shedding model that is in contrast with the high stand shedding model, where the the slope and the basin of present day platform is mostly sourced by grains resedimented from the platform top. Instead, in microbial platform, the largest contribution to margin growth and slope progradation is due to the microbial boundstone on the upper slope. But also this platform have a different behavior with respect to changes in accommodation space. Most likely they are less prone to drowning because they can carbonate production can extend to a deeper window, so they are less prone to drowning. They are probably also less sensitive to siliciclastic input to nutrient level, and in case of relative sea level fall, we can assume that the present day carbonate platform the carbonate production at the margin of the reef is shut down, and we develop unconformity with karst. For the microbial carbonate platform, if sea level falls, even of several tens of meters, as in the Carboniferous with glacial eustacy, the carbonate platform can continue growing on the upper slope, and the platform can prograde independently from the sea level fall. And this summarizes all the example of a high relief platform that I showed you from the late Paleozoic to the Triassic and Jurassic. One last thing is, where do we find in the geological record this platform? It seems that there is a coincidence, because they developed in confined restricted basin with a high seawater supersaturation with respect to carbonate after events of biotic crisis or due to environmental perturbation that allowed microbial mats to develop, and there was less substrate competition. They are often in settings where trophic condition and nutrient level allow the development of abundant organic substrate, either by siliceous sponges or the development of microbial mats. Probably the basin adjacent to this platform were low sedimentation rate and starved, and in some cases even anoxic, and this must have been a type of basin that promoted the microbial precipitation and the development of these high relief slopes. So in conclusion, the present not always is the key to the past, but we need the present to understand the processes that might have taken place in the past. But from the geological past and the outcrop studies I show, I think we can improve the understanding of the present, and maybe also of the future and possible future environmental and climatic perturbation. And what we need to keep in mind is that this carbonate platform can be considered non-actualistic example of carbonate system, and when we interpret them, we need to consider that the carbonate factory has a higher depth extension on the upper slope, and they respond differently to changes in accommodation. And therefore, also interpretation of leeward and windward margin, and what is more progradational, more aggradational. In the case of microbial platform, they have to be revised, because there is not only the Heisted shedding model that has to be applied. Where can we find them? Probably in a specific confined basin with high supersaturation of seawater with respect to carbonate mineral, probably oligo to mesotrophic, and in a confined basin rather than in the open ocean. And with this, I have concluded my presentation. I hope it has been interesting. I've been probably a bit too long. I'm sorry for the time I've taken.
Wonderful presentation. Thank you so much, Giovanna. You are fine for time, and I know that there's probably a lot of questions that people have to ask. I've seen a couple of hands pop up in the participant list, so please type your questions out in the chat. Because we can't unmute you and have you ask them yourselves, unfortunately. So I have a few of my own, but I will get to the chat from our participants first. Our first question, I just want to mention also, please let us know where you're watching from, as we just sort of like to know where everybody's coming. All right, so our first question is from Mazin. He says, very interesting and insightful presentation. Thanks, Giovanna. How different ediacaran microbial carbonate platforms would be in terms of facies variations, knowing that they have not influenced by diversity of the reef buildups biota, same as in the Phanerozoic?
Okay, Chelsea, you have gone, I'm looking for the test. You have gone a little bit too fast in reading. Can you read it slowly?
Yeah, I can go a little bit slower. Sorry about that.
Yes.
Okay, so basically his question, I think, is really just trying to get at how different the ediacaran versus Phanerozoic.
Okay, yes, I found it.
In terms of facies.
Okay, I limited myself to the Phanerozoic because the Precambria is a complex setting. I think there is more skeletal contribution in the Phanerozoic, and I think you have to take into account, first of all, that you are in setting dominated by microbial precipitation, and what counts a lot can be the saturation state of seawater and the setting where you have your carbonate system, because in some cases, especially in various examples of the Precambrian study by Grotzinger and others, you have also seafloor cement and cement precipitation, and on one side. The other, I think I would take into account a lot the hydrodynamic setting and how current energy, weight base, and sediment disturbance can affect the microbial, the various phases of the microbial boundstone in your platform.
Mm-hmm. Absolutely. Okay. Our next question comes from Stefan from Aarhus, Denmark. Hi, Giovanna, super talk. Can you see retrogradation in microbial high relief platforms, or will you just have pure aggradation during fast relative sea level rise?
This is a very good question. I have seen, maybe I can go back. You can still see my slide, no?
Yes.
There, mostly for the Carboniferous case studies, I've seen aggradation during rapid creation of accommodation space. Here it is, rather than retrogradation, as you can see also in this diagram. So there are events when there is rapid creation of accommodation space, there is aggradation. Where instead we have seen retrogradation, sorry if I go up and down this slide, is in the Jurassic, in the lower Jurassic, where there are the coral reef, because the Jebel Budar is affected by thin sedimentary tectonic due to extensional activity for the opening of the central Atlantic. In this case, as you can see in this diagram, actually retrogradation is very important. And here, even though you have a coral reef and microbialites, the system tend to retrogradate because the creation of accommodation space driven by extensional tectonic is too fast to keep on prograding. There is only in this area is called sequence 5, where there is evident progradation. For the rest of the system is aggrading and even retrograding.
Okay.
Okay.
Yes, absolutely. So you think probably without that tectonic influence, you wouldn't see the retrogradation there. It would mostly just be aggradation.
Yes. And in this case, the production rate is probably lower than the Carboniferous example I showed, and the creation of accommodation space is too fast to allow the system to prograde.
Okay, yeah, makes sense. Okay, Mazin says he's watching from Oman. Good to have you. We have Fiona coming from Dorset, UK. Thank you for your very comprehensive talk, Giovanna. So anyone who still has questions, you can please send them to the chat. Please send them to everybody, not just to Sets Online. While we're waiting to see if any more pop up, I had a couple quick questions. So you touched on it a little bit sort of in your conclusion slide, but I wanted to sort of take a little bit more of a broad scope, I guess, to my question. So you mentioned that a lot of the examples that you discussed sort of were preceded by extinction events in Earth's history. So yes. I'm just wondering if you want to say a little bit more about their formation, if you think it's mostly due to sort of like a lack of competition or like opportunistic deposition. Is that the thinking there?
Yes, I think it is both the fact that you have biotic crisis, or simply, as the case of the Dolomia Principale, you have restricted basin with high salinity, even though in other cases coral reef develop. And you having availability of substrates, the microbial mats can expand without grazing by other organisms and have a substrate available. So I think they are there, but you see them little because the substrate are occupied by other organisms. After extinction event, they can just opportunistically take over.
Mm-hmm. So do you think that there's a reason then why sort of at the lower slope end in some of the more modern systems, why we wouldn't see a little bit more of these types of slopes? Sort of, yes, the microbial carbonates playing a part in those lower areas that...
I mean, you know, there are studies, I think rheolids, that showed that there is some microbial precipitation also in present day slope. Mm-hmm. I think it's really et al. 2017. They found some clotted peloidal micrite in deeper areas on slope, but I guess the competition by mollusk, echinoderms that are occupying the substrate but also feeding on microbial mats does not allow them to develop. We see exactly the same in lakes. Where do you have microbial bioherms? In lakes that have hypersalinity or alkalinity that do not allow the skeletal fauna to develop. So there is availability of substrates.
Yeah, makes sense. Okay, moving on to our next question is from Paul Wright, coming from Cardiff. Hi, Paul. He wants to know what the microbes are eating.
Well, this is a complex, I think, and maybe Chelsea can help me here. My experience I've seen so far in looking at microbial mats, not from, unfortunately, a microbiologist's point of view, is that microbial mats are usually several millimeters or centimeters, and they are a community of different type of microbes. And often you have on the surface those that are doing the photosynthesis, so they get the food using solar energy and transforming inorganic carbon in organic carbon. But then below them, there are sulfate reducers that eat by decomposing dead biofilm of other microbes. And then there are sulfide oxidizer, and then going deeper, there are other type of microbes. So I think that, and the Bahamas demonstrate microbial mats can develop also in oligotrophic setting because the community itself is a complete food chain. And they feed on each other. That's why they are mats with different type of microbes, one on top of each other, because they can sustain themselves. That's why, in my opinion, not necessarily this setting they have to be mesotrophic, where there are nutrients to feed the microbes. In the Palaeozoic and Triassic and Jurassic, they were associated with sponges. They were living in sponge tissue, and they eat it, degrading the sponge bodies. So nutrients can be important, but they are not necessary. And if we see microbial mats in lakes, in travertine, all the food chain is already there. They don't need it from sources from outside. In fact, they develop in hot springs, where food is coming from nowhere.
Right. Yeah. So it can sort of end up being a self-sustaining system.
I think so. I mean, you have some doing photosynthesis, some other degrading the dead organic matter of those doing photosynthesis through sulfate reduction. You have sulfide oxidizer, methanogenic, and the community lives by itself.
Yep.
That's why they make thick mats.
Okay, we have one more comment from Stefan. He says, the PF actually precedes a mass extinction event. These PF are experiencing global demise due to a boundary event. So what could
sorry, I didn't.
Oh, the last
PF,
comment.
the Pennsylvanian. Well, he refers to the Toarcian oceanic anoxic event.
Yeah, so he just wants to know what could this tell us about the conditions necessary for the development of that factory.
Okay, the lower Jurassic microbial platform follows the Retian ectangian. We have the ectangian where there are very few carbonates. Then in the Sinemuria and Plinsbachian, the Plinsbachian is basically in the moment in which we start to have a coral reef after the last coral reef that we saw in the Retian. So there is still the effect of the Retian ectangian extinction event. The Toarcian that this he is referring to is oceanic anoxic event. In fact, oceanic anoxic events are indicated here in black. Oceanic anoxic events are global perturbation of the carbon cycle that create biotic crisis and increase in ocean acidification and are related to significant CO2 emission due to large magmatic provinces, but they do not cause massive, for many type of organisms, massive extinction events like the big 5 or 6 indicated here. So yes, what happens is then that the carbonate platform I show you for the Plinsbachian drowns, and then there are no Toarcian carbonates in that system, negatively affected by the Toarcian oceanic anoxic event. But still, you have Plinsbachian microbialite following the extinction event at the Retian ectangian boundary. Did I answer the question? This was the comment?
For me, you did. Stefan, if you still have any more comments or questions about that, just type them into the chat. You did have another comment from Danielle coming from Geneva, and he says that he fully agrees with the views about the microbial development, and that's why they're everywhere. So he says, thank you for sharing all of those great examples. So I agree with that. So I had one more question, actually. If you want to flip to one of your last slides where you sort of had the two comparisons of the shedding, the high stand and the low stand.
Wait, okay. This one?
Here. Yes, exactly. So I mean, this might be a little bit of an ignorant question, but I'm wondering why in system 2 in the microbial carbonate factory, why are you getting less of an input from sort of from that platform top? So if you still have similar sediments up on that platform top, I mean, I totally
you
get
are right.
More shedding,
maybe I haven't been clear. I mean, in a relative proportion. This summary follows studies where it was quantified on the upper and lower slope, the contribution of sediment from the slope itself and from the platform top. It is relatively less contribution because if you look at the sediment distribution along the slope, the production of the boundstone is so much higher with respect to the production of sediment and shedding of sediment on the upper slope that you see a higher contribution. But the platform was shedding and producing, but it was in percentage much less because the production rate on the upper slope was higher.
I see. Okay, so it's not necessarily that there's less shedding off from the platform top. It's just that relative to what's shedding off of the upper slope.
Yeah, one thing that is less in this Paleozoic and early Mesozoic case study is the amount of carbonate mud. Present-day carbonate platform produce a lot of mud that we do not see in this Asian platform. And there are two reasons. During the late Paleozoic and early Mesozoic, there were not the typical green algae that you have now on the Caribbean platform like Halimeda, Pellicillus, that produce a lot of fine-grained sediment. There was less bioerosion in the late Paleozoic and early Mesozoic. The explosion of microorganisms that bore and produce detrital carbonate mud due to boring was less. And there was no pelagic rain because we know that planktonic foraminifera started in the middle late Jurassic, and the calcareous nanoplankton, the first example are late Triassic, but the explosion from the late Jurassic and early Cretaceous. In fact, the chalk is a Cretaceous very thick deposit. So there is definitely less production of carbonate mud on the platform top and no calcareous plankton. So the slopes have less matrix and are dominated by this in situ boundstone and the resedimentation of this boundstone.
Okay, yeah, that makes sense. Okay, we have one more comment from Stephen coming from Derby, England. He says, thank you for the terrific presentation. He's going to point all of his students to the recording, and he's really looking forward to this, the field guide. So thank you to all of you for making it. I'm also really looking forward to the field guide. All right, so Giovanna, thank you very much for this wonderful presentation and sort of overview of these microbial carbonate factories. We are very happy to have had you here this week. And everybody come back next week. We're going to have a presentation by Kim Singer on a new Svalbard database. So we will see you then.
Thank you very much to all of you and for attending the presentation. Bye.